Okay, are we in the next session yet?
I think
Good.
Yeah.
I think we are. Okay, so it's my great pleasure after Kyle Cranmer's stunning talk from New York to introduce Zeynep Akata to you. She just sits a couple offices down the hallway. She is our first new faculty member hired from the Cluster of Excellence, and she started in fall on a professorship for explainable machine learning. She works on zero-shot learning, on verbal explanations of visual decisions, and so on. I'll give you a brief background before we just go right into the talk. So Zeynep did her PhD in 2014 in Grenoble, and then did a postdoc at the MPI for Informatics in Saarbrücken. Also was a visiting researcher in Berkeley before she became an assistant professor at the University of Amsterdam, from where she actually came to Tübingen, which made us all really very, very happy to have her here and kind of contribute to our community here. She just told me that it's really a new talk about an entirely new topic, and I'm really looking forward to hearing about your latest work.
Thank you for the nice introduction, and thanks for the invitation. It's very nice to be in Tübingen, actually. It's, I think, one of the best places to spend the lockdown, I would say. Today, I will talk about our ongoing work on learning decision trees recurrently through communication. This is a project that we started when we were in Amsterdam, and then after we moved here, most of this work has been conducted within the Cluster of Excellence. And it's a joint work with Stefan Alanis, a PhD student in my group, and Diego Marcos. He's a postdoc who is going to visit us through the ELIS program. Okay, so in this project, we would like to provide human understandable explanations of the decision path taken by a decision maker. And the decision is going to be made by classifying an object that is shown. An example is shown on the right. For example, our model receives images of different types of animals or different types of birds or different types of objects. This can be as many as 1,000 classes that appear in ImageNet, and the model is supposed to give one single label to every image that it receives. What we have introduced to the decision maker is that it is supposed to tell us how it reached a decision, and we have basically implemented a decision tree mechanism. And our inspiration comes from communication. So in our framework, we have two agents, the blue robot and the red robot. One of them, the red one, is able to see the environment, so has access to the data. And in principle, it is the perception module of this network is perfect, basically. It's able to classify every image it sees. But we restrict it by asking questions. So the blue agent comes to a decision of not being able to distinguish between four different kinds of classes for this image. And then it says, it asks if this object is furry. That already eliminates half of the classes. And the answer is yes. So the class can be either a cat or a dog. The car and the plane are eliminated. And then the next question needs to be formulated in order to eliminate as many classes as possible again. Does it have whiskers? And the model needs to say no, because it's a dog. This again eliminates half of the classes, and the decision path is shown on the left. So there are previous works who have proposed solutions to this problem. One of them is deep neural decision forests. This is the closest work to ours. Here, the authors propose to learn the decision nodes and leaf nodes of a decision tree with a neural network. They have a CNN and a fully connected network at the top. And then the trees use soft routing, so all the leaf nodes are considered, as opposed to our hard routing, which only follows a single path through the tree. Here we have a deep CNN with parameters, and it predicts routing probabilities between 0 and 1 of each node. And then the leaf nodes are vectors that represent class predictions, so class probabilities for an input. And they fall into one of these buckets, basically. And by multiplying all the routing probabilities of the path for each leaf node, the weight for the leaves are calculated, and the final class prediction is obtained by a weighted sum of the leaf nodes class probabilities weighted by their routing probabilities. And then we have another related work, adaptive neural trees. Here, they are adaptive neural networks that are structured like a tree that grow during training and with the complexity of the problem. And each input gets routed through a different set of neural network layers. And these layers can be thought of as neural module networks. They are also very similar to this other paper, and they are classified at the leaf node. On the left, this is taken from the paper. It's an ANT, adaptive neural tree, and each black dot is a neural network layer that transforms the input, and are the white nodes that is a router that decides whether the image or the data should fall to the left or the right, and that we have gray nodes, and it's a solver that makes the final output prediction. And on the right, we see 3 different ways of routing that they do. First, they can either split the data, they add a router to split the data, or they deepen the transform by adding a transform operation, or they just forward the whatever is in the input to the output. The last related work is here the authors, it's called Emergence of Language with Multi-Agent Games. We also integrate language to our framework. And here in this paper, they learn to communicate the identity of an image in an image reference game from scratch by sending discrete tokens. And they use Gumbel softmax like we do. And they use natural language. So here in this picture, the sender agent encodes an image with a CNN and an LSTM, these blue boxes, and this should identify the image among a set of images. And the receiver, this agent, processes the tokens and compares compares the obtained information with the reference images, these 3 images, to identify the most similar one, basically. And here in this framework, the communication is one-sided. So in our work, we have 2 different agents, like I mentioned, a blue agent and a red agent. So the first agent is called recurrent decision tree, and here we iteratively aggregate information into an explicit memory, shown in gray, to be used to discriminate the correct class label Y from all the labels, the vocabulary, basically. It's a fixed vocabulary, and initially there is no prior information about the object. And then to gather information, RDT agent sends a query message like this to the ABL agent. So the query is constructed with an MLP. I will describe the details in a bit. And then so the next stage is the ABL agent takes this question and it answers the question about the image. because it knows the answer of all the questions, basically. This is because of the perception module being perfect, it's able to answer all of the possible questions, but just it needs the RDT agent's question to be able to give the answer. And then using this answer, the RDT agent updates its policy and its memory. And this is one iteration of the agent-to-agent communication. And as you can see on the left, as a byproduct, we see a decision tree. Okay. So our communication protocol is attributes. We use attributes as explanations. And attributes are visually discriminative properties of objects. Like if we have two example birds here that are eastern bluebird and cardinal, we see that so these attributes are like blue crown, white belly, black eyes. Some of these attributes are specific to one of the class only. And some of these attributes are common. So both of the vectors that represent these classes are going to have the same value. And then some of these attributes can also be in between 0 and 1. So at each communication step, our RDT agent chooses one attribute and requests the presence or absence of this attribute in the image. And then the other agent provides the binary information of whether this is present or not, based on its own prediction. And we chose this communication to be binary because it's much easier to interpret for the users than probability values. So if we go into details of the model, the the discrete messages of the recurrent decision tree is constructed as follows. We need these messages to be discrete signals because we want to train them, but also differentiable because we want to train them end to end. And Gumbel softmax allows us to sample from a discrete categorical distribution. And we sample this GI from a Gumbel distribution and then compute a continuous relaxation of the categorical distribution. And then the model decides on an attribute, which attribute to request, basically by the index CT. And this is done by an MLP. And then the second component is the memory mechanism of the recurrent decision tree. We implement the 3 states as an LSTM. So the LSTM hidden states are encoded here. And we have an explicit memory that keeps track of the previous decisions, basically. And we update the state with the queried attribute CT and the decision DT. So MT as a summary contains all the binary attributes that are communicated from the first step to the last. In this example, the first answer was yes, the second was no. And then the LSTM also keeps track of the history of the communication. And after each communication loop, the attribute CT and DT are used to update the states. Okay, and now the decision tree. So I mentioned that the decision tree is a byproduct of our framework. We predict the class with this explicit memory CT, and this is just a simple MLP, multi-layer perceptron. At each step, this explicit memory is used to predict the class label. And since the primary objective is classification, we maximize the classification performance by minimizing cross-entropy loss of the predicted class probabilities. This is a standard formulation. Okay. And the next is the attribute-based learner agent. So here, this agent is a deep neural network. It could be ResNet. that is pre-trained with a large data set like ImageNet, and it is able to predict class labels and accordingly all the probabilities of different attributes. So in this example, different colors represent different attributes, and yes, no are the probabilities of each decision. So we discretize these probabilities by using a temp softmax. This is just we have a temperature, and based on basically a threshold that we set, this is a parameter to tune. We decide on which attribute to be present or absent. And then the model returns the decision dt based on this query index that is requested by the previous agent. And this is used to update the memory. The loss function is basically, we optimize the classification accuracy, and we also optimize, we add an attribute loss for additional explainability. So this loss function ensures that we have a decision tree that makes the model transparent, and then the attribute loss is included to make the explanations human interpretable. That in a way attaches a name to a decision. Okay, I will show some example results. ImageNet is the largest scale dataset available for image classification. It contains 1,000 classes. It's a 1,000-way classification. And the black bar is the state-of-the-art results obtained with non-explainable deep neural networks. The blue bar is a classical decision tree. And then this is neural decision forest, is the method that I had mentioned. As I mentioned, it explicitly models the decision tree by mapping each inner tree node to an output neuron, and it has soft routing probabilities, and it uses exhaustive tree traversal. But it is still very impressive that the accuracy is very close to the state of the art, and our model doesn't use as complicated loss functions, but it also reaches the same accuracy. And then we also have experimented it on Caltech UCSD BERTS datasets along with other datasets actually. And this dataset is interesting because it contains 200 classes of different types of birds. So classification accuracy is a little lower, and the decision trees don't work as well because we have a very wide and shallow tree, basically. And our model outperforms the previous ones. And also, we can use attributes in these examples. So we see that by adding attributes, like by adding name or human interpretable explanation to the decision tree branches, we don't lose any accuracy, or very slight loss of accuracy, but it's much better than the explainable decision trees. This is by adding attributes to the plain decision trees. Okay, we also made a comparison with the neural decision forests here in the sense of how the tree grows with the increasing accuracy. Basically, the model needs a much deeper or many more distinct binary nodes to be able to classify images on ImageNet, these 1,000 categories. So the number of distinct binary nodes is computed in this log scale, so it's quite a large number. In our case, we can evaluate the method, so we can train it once and evaluate it on different tree depth. This is one of the advantage, and also it reaches the same accuracy as deep neural networks by using much less distinct binary nodes. And the same behavior is observed on other data sets too. For example, the BERTS data set. Here we show that by increasing the weight of the attribute prediction loss, we lose some accuracy, but it's not that much. And with the given benefit of human interpretability on that using the attributes, this is basically, it doesn't hurt much the accuracy. And I also would like to show some qualitative examples. So these images are taken from Caltech UCSD BERTS dataset. As I mentioned, there are 200 classes, but I'm showing only 8 of them here. This dataset is very, it requires experts to be able to identify these birds. Basically, they are very similar to each other. And our decision tree, our model, has made this decision of separating these classes into 2 different categories based on the underparts color. As we can see on the right, all of the images don't contain objects with white underparts, whereas maybe it's not all visible here, but we can verify also from the other images of the dataset that these objects indeed contain these properties as yes. And then in the second level, has breast pattern solid applies to these images as yes and these images as no. And then we can basically show the decision tree in many different layers, but I have restricted here only 3 levels. And there are some interesting observations, like here, for example, in the last layer, has crown color black. In this case, this object, so these 2 objects indeed have many different properties probably, but one of the distinguishing properties is the crown color. And here, this doesn't contain a black crown, and this does. So in this way, by showing how the decision mechanism is structured, we can go back to whether or not the decisions has been done correctly. And one example to this is we can follow images like this. These 2 images come from the same class, basically. And in the first step, white underparts is the most distinguishing property. This is selected by the model, and both of these images fall into the same bucket. And then we follow the decision path, and we see that this image was classified incorrectly based on the black wings property. When the bird is sitting, you can see the black wings, and it is correctly predicted. But when it is flying, you don't see much black wings, so the model has gotten confused, and it got classified this bird as blue kingfisher versus green kingfisher. As a conclusion, in this work, we are learning decision trees recurrently through communication, and we adaptively change the tree depth at test time, and this allows scalability. And we also add interpretability without losing much from the accuracy. We maintain the accuracy of deep models. And we also allow inspecting individual examples because we have access to how their attributes are predicted, basically. Like I mentioned, this work is in collaboration with Stefan and Diego, and we are preparing still the final version of this paper. Some references that I had mentioned throughout my talk, and I would like to thank you for your attention. If there are any questions.
Thanks a lot, Zeynep, for the great talk, and thanks for sharing some unpublished material. I think it was a very interesting look at what you're thinking and doing right now. We do have a couple of questions, and so the first one is from Matthias Hein. Yeah, so the virtual clapping is always a bit bleak, but there's also lots of clapping going on. I maybe just ask the question for Matthias. So what happens at test time if you show an image that's not in the distribution? Let's say you put a bird of a dog in your bird classifier. Have you tried that?
So so one thing that I didn't mention is the model. So the decision tree or the communication model is trained for every data set separately. We don't have one global mechanism and then we apply it to all the data sets. But in case of, for example, in ImageNet, we have a different decision tree. In birds, we have another one. And if, for example, a dog image is given as an input to the decision tree or the communication model that is trained using birds, then it's going to predict attributes of birds. But I would argue that the model that is trained on ImageNet should be able to generalize to many, many different classes, unless the images are not natural images, but for example, sketches or paintings or something. Then I don't know how the behavior would be. Probably because the classification accuracy is very low, maybe the decision nodes won't make much sense. So we rely on the accuracy of the attribute-based learner when we are building the decision tree.
Mm-hmm. And maybe, so following up on that, a question by Erik Reidel here from our philosophy lab. So what happens if the class cannot be really characterized by a set of attributes by the algorithm because maybe the feature space is too poor? Can that even happen?
Yes, it can happen. Like I mentioned, in different domains, like for example, if your input is a sketch, then maybe all of the attributes are not visible or not recognizable, and then then the model is still going to be able to output some attributes, but maybe it's not going to be correct.
Mm-hmm. Okay. So there's a couple more like these technical questions, but I go through them.
Also, the audience can send me emails if they like, or come to my office to have a discussion. I would be happy to.
Cool. Yeah, thanks for the offer. So have you looked at unbalanced class probabilities? Let's say if there's one of the classes that's really much less present, something that we would, for example, if we thought about an application in the healthcare sector that we might have, with healthy and diseased.
Yes, this is a very good question. So we haven't evaluated this model on many different interesting scenarios, and unbalanced dataset problem is a real one, and we haven't tried it. I mean, the only thing that I can say is this model is the one that is trained for ImageNet also needs to handle imbalanced data sets. Basically, ImageNet also doesn't contain, doesn't have a balance in the in terms of number of images per class in the data set. But of course, this is just one example. And in the medical domain, although this is very interesting, I don't have any experience, so I can't really say much.
Yeah, there's probably also no good data sets readily available.
Also, and also maybe the So we, like I said, we rely on the performance of the deep neural network, and we use RedNet that is trained on ImageNet. And if there is no kind of perfectly performing deep neural network or well-performing deep neural network or another decision maker on the medical domain, this is going to be the bottleneck when it comes to introducing explainability.
Cool. Maybe one very quick final question. So is the communication lossless between the agents, and what would happen if there was loss? So if there was an information bottleneck or something like this. So there's a question by Charlie Wu.
Yes, very interesting question. So we assume that the communication is lossless. So we assume that the agents are consistent. Basically, they are able to. So one of them is going to ask a question, and the other one is, if it knows the answer, it's going to answer it perfectly, and it's going to be able to communicate the answer perfectly. So we have some prior work on lossy communication, and there we were basically thinking more in the lines of theory of mind, and to form to form a mental model of the communication partner was the most important contribution of that work. And if Charlie comes to Tübingen and would like to discuss with me, I would be very happy to do that.
Okay.
Or to discuss about this other paper where we consider this problem.
That sounds exciting. I just learned that I was ahead of time, and we do have some more time for more questions. So I am going to ask a couple more.
Sure.
The communication channel that you use, does that have similar attributes compared to human language? Like, I don't know, some attributes get communicated a lot or are used a lot, or and others are maybe only very rarely. Do you have a similar distribution or kind of entropy properties there?
Yeah, this is another very good question. So we have observed that color-related attributes get communicated more often, and this is probably because it's so the model is trying to differentiate as basically as many classes as possible, to divide the data set into equal bags, and apparently color-related attributes are more discriminative to do that. But this could be a dataset bias because, for example, in case of birds, indeed, there are many more color attributes than shape attributes, and those color attributes are shared among the kind of the subset of classes that are similar to each other, like different types of sparrows, for example, share certain properties, and then some of the colors never appear in this bag. Yeah.
And the final question I have in here, so have you ever observed the presence of spurious or of spurious attributes that maybe are not genuine attributes of the class, but just are associated, or there's a confounding effect in the particular data set? Have you thought about this question?
Yeah, not really, but indeed, if some attributes are, although they may be present, but they are not class specific, or they don't help with reducing the classification loss, I'm guessing that they are not going to be predicted by the perception module. Yeah.
Okay. So one thing that I would be curious about, have you? So I mean, classifying birds is very interesting, and it's also sciencey. Have you thought about other applications in science where such communication-based or agent-based engines could be useful?
Medical imaging came to my mind. Of course, if, for example, in the scenario of medical diagnosis for, I don't know, brain tumors or something, then this kind of a interpretable decision mechanism would help, maybe not the expert, because they are already able to see every detail that reaches the decision, but maybe a slightly a more novice user, either the patient or a non-specialist doctor. Then having a decision tree or an interpretable decision-making mechanism along with the explanation of or justification of why every decision was made that way, or labeling these decisions, would be very interesting. Yeah. Hopefully it will be one of the projects that we will work on here in the cluster.
Yeah. Okay, so that's all. Thank Zeynep again for the very nice talk and the presentation. We will now take a 20 minutes break and come back here at 4 with an experiment. With an experiment where we try to showcase a bit the Innovation Fund projects that we have in the Excellence cluster. So the Innovation Fund projects, these are is our internal funding line where we support PhD students or postdocs in particular collaborative research projects, and each of them is giving a very short intro to what they're working on and their first results. So if you're curious about that, join us back here at 4 p.m. And then later in the afternoon, we will continue after another break at 4:30 with a talk by Jakob Macke, who is the second new professor here in the Excellence cluster. With that, enjoy your break. Grab some coffee, enjoy the sunshine, at least in Tübingen, it's nice and sunny, and then make sure you're back at 4. Thanks a lot.